Alright, welcome back again in this video lecture for the course ABE161. Now in this video we will start our new topic on tension members. In starting this topic, I'd like to give an overview about these tension members, and then we'll get into the details and code provisions of these tension members later. So, tension members are structural elements that are subjected to axial tensile forces. If you recall in the course in structural materials or mechanics of materials, in axial loadings you can either have compression or in tension. Now, for us here, we'll only focus on members subjected to axial tension. Now, these tension members, they are actually used in various types of structures, such as in some truss members. So let's say in our roof trusses. Now, some members here, they're actually under tension, and other truss members are in compression. Okay, so how do we know if they're in tension or they're in compression? Now, actually, if you have a downward loading, let's say this loadings comes from the roof loads, now you're going to have a deflection. Okay, so let's say this is the deflected shape. Of course, you're gonna have let's say something like this, and the members in between will have something like this. Okay, so starting with this original, let's say original length, you're going to have an elongated length. So meaning that these members, actually these diagonal members, they're actually in tension. Okay, and trusses, they're also used in bracings of frame buildings. Let's say we have a square frame, and sometimes there are used these tension members. They are actually used in the braces. Okay, so this brace can be in tension or it could be in compression depending upon the loadings experienced by this structure. And also tensile members or tension members, they are also common in suspended cables, like for example a platform. Okay, let's say this is a platform, and this platform is actually being supported by cables. So meaning if you have a load on this platform, then you're actually inducing a tension force on these suspended cables. Okay, so those are the typical applications or common applications or situations where you can find these tensile members. Now, what are the steel sections that are commonly used for trusses? You would notice a example for residential housing. You would see an equal leg angle for the members of the trusses. Okay, and sometimes in some, let's say, wider span of these trusses. So when I say span, then from this first truss to the second adjacent truss. And for meaning if you have a wider span, then meaning that you have a higher loadings, and therefore you have in some situations they use the angle, this steel shape in this configuration. So it's a welded back-to-back configurations. Okay, just to increase the section capacity. Now in bridges, you would see other types of sections such as could be the W shapes or other build-up shapes, and probably channels, then bars. Also, it's also common to use bars in these tension members. All right, so now let's go on to the derivations and code provisions for these tension members. Okay, so for the derivations, I will talk first about the limit states. Recall that these limit states, we have already introduced this in our topic on introduction to steel structures. They're actually common, or they're actually the approaches, the approach for the analysis and design, meaning that these limit states are something that they're the conditions that governs the sizes or the analysis of your steel member. Okay, so something like they are the limiting points, or just limits relating to the failure of the member. Okay, so for tensile members, we have actually two limit states. We have yielding in the gross section, and we have rupture or fracture, okay, rupture in the net section or net area. And there's also another one here that's um, regarding the slenderness. Okay, so we can just write the slenderness provisions on slenderness. Okay, so take note, I've written here 1, 2, and 4. So meaning there's actually another one for the tension members, and it's somehow related to not just the tension but also the shear. So something related to both shear and tension, and that's what we call the block block shear rupture. Okay, so these two, they're actually um, they're just actually limit states in pure tension, whereas here this one, the block shear rupture, involves a failure on shear. This one is with regard to the geometry. Okay, so let's discuss first the yielding in the gross section. Okay, so let's say we have this bar, this angle bar, and this angle bar is, let's say it is attached to a gusset plate. Recall that a gusset plate is something like a plate uh, that's being used in the joints for connecting the members. Okay, so let's say we have this angle bar and it's being subjected to a axial force or a tensile force P. Now, when you're trying to, let's say this is our tension member, and this one is our gusset plate, and this one, let's say we have a bolted connections. Okay, so once you're actually pulling this member away from this plate, then the failure could be, if we draw this in a side view, okay, so once we're actually applying the loads, then it is possible that there's gonna be yielding somewhere on the gross area. Okay, so let's say there's gonna be yielding. So let's say yielding in the gross section or area. Okay, so take note, um, recall that yielding is not actually, um, it's not that the material is breaking apart, it's just actually passing this yield point. Okay, so recall this stress strain diagram of the steel. Okay, so Fy referring to the, sorry, not this, not here, this should be the Fy, and here is the ultimate, and somewhere here that could be fracture. Okay, so when I say yielding in the gross section, this section somewhere, or let's say anywhere along this gross area, it could be yielding. Okay, so that's one of our limit states. Okay, and when we say gross area, then we're actually taking this cross-sectional area without these bolt holes, or not at the section of the bolt holes. Okay, and then another failure, if we subject this, then this tension member in a actual force, then it could be that the the section right here where there's the presence of bolt holes, then it can actually uh, break apart. Okay, so could be something like this. So it breaks apart or it fractures. So meaning this failure would be the rupture or fracture in the net section. Okay, so take note, this one is yielding in the gross area, meaning that we're not, I mean, it's in the area where there's no bolt holes. But this one, it could be because of the reduced cross-sectional area, then it can it can fracture in that section. Then the black shear rupture is something like this: a block or a chunk of of these tension members is actually um, fracturing, or is being separated from the rest of these tension members. Okay, so that's what we call the block shear rupture. Okay, so in detail, we have this equation, this elementary equation of stress, and the stress is equal to force over area. Now, if we are trying to find the safe, let's say the safe load, the safe tensile loads for these tension members, then we have to examine the limit states, the capacity of the tension member in each limit states. So, meaning we can rewrite this as force is just equal to stress times the area. Okay, so this one would relate to the strength of the member, and this one would relate to the cross-sectional area. Okay, so now let's say we have this. Let's draw this again, or let's draw another. Let's say another section or steel section with bolt holes. Okay, so let's say we have an unequal leg angle, and it has 4 bolts. Okay, so meaning if we try to cut a section along this bolt hole, and we'll try to cut a section away from this bolt hole, So let's say this is section A, and then let's say this is section B. So if we try to draw this section, okay, so you would notice that this is your cross-sectional area, the shaded area. Okay, so the shaded area is actually our net area, and it's basically the gross area. Okay, so A sub G, that's the gross area, minus the area provided by this bolt hole. Okay, so let's say area of bolt holes. Okay, so how do we compute this area of the bolt hole? It's actually the okay, so area of bolt is equal to the diameter. Okay, so this is the diameter of the bolt. So let's just say, let's just write D sub B times. Actually, the code requires us that when we're analyzing these tensions, this tension member, then we have to add a clearance. So the bolt diameter plus the clearance, and the clearance is it's specified as we'll take it as 2 mm, so plus 2 mm. Okay, so diameter plus 2 times the, of course, the thickness, or let's say the width, or let's just say the thickness. Okay, so meaning that A net is just simply AG minus the area provided by the bolts. So if it is if there are 2 bolts in this section, then you can just multiply it by the number of the bolt holes present. Okay, so where do we get this gross area? We can get this from the table, or if it's just a flat bar or a flat plate, something like this. If it's a flat plate and you're given by this, let's say it's 6 mm by 100 mm, so meaning that the area is just simply, you can multiply that 100 times 6, so that's going to be 600 mm squared. Okay, so for steel shapes, where there's data that's tabulated or can be obtained from the table, then you can just refer to the table for these cross-sectional dimensions. Okay, so now let's discuss this back again to the yielding in the cross-section. Now, for the yielding in the cross-section, our equation is the factored this factored capacity P sub n is equal to the reduction factor times Fy times Ag times the gross area. Okay, so that's how we're going to evaluate the capacity. Okay, for the rupture in the next section, in the net section, we have the factor close is equal to the reduction factor times the ultimate ultimate strength, that's F sub u times A sub n. That's the net section. Okay, and for this one, we will we can just calculate it using this. So R sub n, meaning that's the That's the notation used for the capacity. So R sub n is just equal to, or we'll just write it here again. Uh, for the yielding in the cross section, we have the factor capacity is equal to the reduction factor. Okay, in some notations, there's a subscript t for the in this reduction factor. So that means reduction factor in tension, Fy times Ag. For the rupture in the net section, we have the factor capacity is equal to the reduction factor F times the ultimate strength times the net area. Okay, so you'll see the difference that this one is based on yielding and gross area, whereas this limit state is based on the ultimate strength and um, the net area. Okay, so and also the difference is this: the reduction factor for yielding is 0.9, whereas this one, the reduction factor is 0.5. Okay, so rupture in the net section is actually we can call it a sudden failure. So that's why we have this a much lower reduction factor. And in the block shear rupture, it's actually um, the symbol used is R sub n, and it's going to be the minimum of the two conditions. Okay, so since this is the factor capacity, then it means that we have to apply the factor here. So 0.6 Fy Agv plus U times Fu times A and D. This one is 0.6 Fu A and V plus UPS Fu A and D. Okay, so there's actually a lot of new terms here. Now, for example, AGV, that means that's the gross or area, or let's say gross area in shear. Okay, that's V, that's gonna be shear, and this one gonna be net area in shear, and this one would be net area in tension. Okay, so this one to net area in tension. Okay, so we notice that this second term right here okay, so this second term in both conditions, they're just actually the same. And by the way, the actual before that, I think I have to explain first what's this AGV and ANV in a picture. Okay, so for example, we have this let's say this plate, and if this plate is, let's say it has 6 bolt holes, then you're loading this, then it's possible that you're actually part or a block of this member is actually ripping off. Okay, so that's one. So once you're trying to, okay, so let's say there's a gusset plate here, so that you can imagine that there's something holding this member. Okay, so when you're trying to pull this member, then this, let's say this part is actually um, ripping off, and probably this part too. Okay, so that's one failure. Okay, so let's say this is failure 1. It's also possible to have a failure something like, instead of the outer part or outer chunk is being ripped off, instead of that, what's being ripped off is this center part. Okay, and probably it's also possible to have this failure. Okay, so let's say this is failure 2, this is failure 3. Okay, so again, a block shear rupture is basically a failure of the material wherein a part of a material or a chunk of a material is being ripped off or ripped apart from the main member. Okay, so it could have possible failures. It could have multiple modes of failure. It could be something where the outer part is failing, or in this case, failure number 2, the center part. The failure number 3, it could be that this part is actually failing. Okay, so if we try to draw that in a three-dimensional view, okay, so this is actually the shearing area or the sheared area. So let's write this is A um, for shear, and of course there will be another area here at the bottom, and that's gonna be the area for shear. Now again, if we say A N for shear, then meaning that we have to uh, minus the bolt area, bolt hole area. And if it's just AGV, then meaning it's gonna be uh, just the gross area. Okay, and then for the A and T, we draw that in the other view, that's gonna be something like this. Okay, and then this one would be the net area for tension. Of course, if you minus this, then that's going to be the net area. Then this one, area for shear. Okay, so our equation is this, that the capacity for block shear capacity, we have condition of either 0.6 Fy times the gross area for shear plus this terms, and whichever is the minimum, then that's the ones that's going to govern. Now actually the main notation, the main notation for the block shear is actually written in this way: V Rn is equal to V times 0.6 Fu A and V. This is the second conditions here, second condition here. Okay, plus, sorry, it should be here, plus U UBS FUA and D. Okay, must be less than or equal to the upper condition here. So meaning that this one is the limiting, something like the limiting value. That should be 0.6 Fy AGV plus UBS FUA and T. Okay, and also the strength reduction factor here is taken as 0.75. Okay, so since it's a fracture, it's a sign of failure, then it has a lower value of the reduction factor. Now, also, um, what else? This U term here is just actually a term wherein if the tension forces or the tensile forces is uniform, then UBS is equal to 1.0. If not, if it's non-uniform, then that's going to be 0.5. Now, in our let's say homeworks or sample problem, unless otherwise specified, we'll just assume a 1.0 value. And lastly, we're going to talk about the slenderness limitations. Now, for slenderness limitations, um, slenderness ratio L over R, um, the L over R, so R mean should not exceed 300. Okay, so that's just the it says preference or preferably should not exceed 300. So meaning this is the length of the of member, and this one is the radius of gyration. Okay, so for this one, the radius of gyration, you can actually just go to the table and obtain this value. Alright, so in the next video, we will do a sample problem for this calculation of capacity of tensile members.